What's up everybody, this is Cakez and welcome back to another tutorial in which we create an input system with rebindable game actions or keys. So to give a simple overview of what we're going to do, we will gather the keys from Windows and Linux into some sort of table that is a generic input key code table, and then we will map the Windows key codes to our generic key codes because we want to have, or if you want, we want to use generic key codes in our engine and not have to worry about that, oh, this Windows key code might not work on Linux or on Mac, right? And so what we want to create is a table of key codes, which is what I'm going to paste in. Basically what I have here is an enum key code ID that references most of the key codes or most of the keys that we would like to have in our game. Like maybe you want to have more, but it's mostly everything that you would want to have. Now, I'm not going to go into controllers for now. That will be in another tutorial, if at all, because I have not touched that myself yet. Below that, we define a struct called key. This key will hold different states. For example, if it is down right now, if it is just pressed, just released, and how many times it has been pressed this frame. This half transition count means that a key, when it is up, and this is the keyboard, a half transition would be when you click and press it down. That is a half transition down. And then another transition, half transition down, would be when it goes from down to up. So basically an entire transition is down and up, and half a transition would be down, and then another half transition would be up. But you notice that we have these bool 8s here, which means we have to go into the schnitzel lib, and then in the defines, we define a character to bool 8. And then if we switch back to input, the error should be gone. And then quickly, we take the input right here, and we move this down below the key code and the key, because we are going to change it. First of all, we are changing the screen size to an I vector 2. Okay, and I have pasted in the next sections. I think it's a little bit easier this way. We want to track our mouse position on the screen. And in order to do that, if we want to know how much they moved from point A to point B, we need to keep track of the previous mouse position. And then since the screen, and we covered that in the last tutorial, the screen has a different coordinate space than the world, we also want to calculate the world mouse position at the same time as we calculate the previous mouse position or the screen mouse position. And in order to do that, we will store that in the input as well. So otherwise we would have this function that would always do the calculation for us. Might as well waste a bunch of memory and then store that here. And then at the very bottom we have the keys that we want to look at. And then right now we only have input globals here. We also want to have functions that tell us, did a key just get pressed, released, is it down, something like that. And in order to do that, we create another section. We call that input functions. In order to know if a key was pressed this frame, we need to first of all get the key, and then we need to check whether the key is down. And if the key is down, then we need to check if the half transition count of the key is 1 or the half transition count of the key is greater than 1. So basically, if the key is down, then the key must have moved from the up state down to the down state. That means 1 half transition. Or if it made more than 1 transition or more than 1 half transition, it means it was either down, moved up and down again, or it was up, moved down and went up again, or more times, right? And so it was definitely pressed this frame at least once. And the same thing holds true for key released this frame. We want to check whether the key is not down, and then the half transition count is 1, and then the same thing holds true for whenever we have more than 1 half transition. And the simple key is down is just indexing into the keys and checking whether this is down. The reason why I'm creating these functions is so we don't have to index into the input all the time. And we have wrapper functions if we decide to change anything or maybe rename these keys, which we won't, but you never know, right? And so I like these wrapper functions more because they hide the data a little bit, and yeah. It's a cool interface. Also, I like yellow. So, okay, now that we have these keys, we also need to collect the input from the layer, from the platform layer. And in order to do that, we switch over to the Win32 platform file. And in the callback, the Windows window callback, we first have to fix this error right here, since we changed this to a vector 2. So instead of screen size X, we do screen size .X and .Y. Okay, and then I pasted in another one, of course. We want to look for the events of key down, key up, and system key down and system key up. If we find any of these events, we check whether the key is down, and then we keep track of the transition count. We increase that by 1, and we store the is down state in the key. And then we check whether the key is just pressed or just released. And in order to do that, we check whether, well, the key is not pressed already. We haven't pressed it yet. Or the key is not down beforehand, but is down now. Basically means it was up and we have pressed it down. That means we just pressed it. And or the key was not pressed before and the key is now down, which means that it was obviously just pressed. And then for the released option, we have basically the same thing but inverted, which means the key was down and it is not down now, which means it was down and then it went up. Okay, and you might have noticed that we have this key code lookup table right here. And this is what I was talking about earlier. We want to use our generic key codes, but they will not align perfectly with the Windows key codes. The numbers will be different because every key code is just an integer number. And in order to make sure that we can just use our key codes, we need to have some sort of lookup table that tells us this Windows key code is actually the normal key code A or B or C. And so in order to do that, we need to create a function, and I call that fill in key code lookup table or something. And we're going to add this at the very bottom of the file, Win32 platform. But the function is actually a platform function, which means Windows and Linux and Mac, they all have to implement this function because they all have different key codes. For example, we are mapping the Windows mouse buttons, VK mouse buttons, to key left, right. I have a mistake here, lol, that's middle. Let me fix that real quick, lol. And you can see that we are mapping, make sure that the middle is correct, by the way. And you can see that we are mapping all of these Windows key codes to the generic key codes that we defined in our input file. And in order to complete this, we first have to save and then define this key code lookup table. And we do that in the main, right between the core, GL core, and the platform header file. It's just going to look like this: a static key code ID key code lookup table with the amount of keys that we have. And this key count is set to 255. And while we are doing this, we might as well also fix the input screen size right here. And this is also something that I would like to talk about. The first time a window is created, this WM size event happens, which means we set the screen size on the input the moment we create a window, which means we don't have to do this. This can go away. And then at the same time, since we are using a certain type of game world, we have a certain size of our world, I would like the screen to be a multiple of that world since we are using pixel art. We are going to get into more scaling in the future, but for now we have a base width of 320, and if we multiply that by 4, we get to 1280. And the same thing holds true for 160 multiplied by 4, that is 640. Okay, and so we are going to create the window, and while we are in the main function, please make sure that you also call the platform fill keycode lookup table function. And also please make sure that this platform keycode lookup table function is not only called here, but also defined in the platform header file. So go into the platform header file and then paste that in. It is a void function. And now you might have noticed the GL renderer is red. That is because we changed the input screen size. So go in here, and at the very bottom in the render loop there should be, we access the screen size here, right? We want to do screen size X and screen size.Y. And then we also want to get screen size X and screen size Y in here. Okay, now we should have no more errors in the key code gathering of input. And we also want to gather input for the mouse. So, and this is the input for the mouse. Basically what we are looking for is an L button down, an R button down, an M button down, and this is left, right, and middle, down or up. And then we do basically the same code as up above with like a little twist. We check if it's down or not. And then we also get the mouse code, which is a somewhat long if check. And then we do basically the same, because in my opinion, a mouse button is a button. Basically that is the same code. And now that we have this code, we need to make sure that every time we have used the input, we also clear the input, which means that whenever we update our window, and we are not doing that right here, but in the update window function, we want to update our input. So I want to put this message stuff into its own thing. This happens at the very end. First, we want to make sure that we clear the transition count and the just pressed and stuff of every key. We do that in this for loop by going over all the keys and then resetting everything to false, aka 0. And then we want to gather new input. Basically, we have the message queue, we peek the message, translate and dispatch them. That's what we did before. And then the last thing is we want to get the mouse position. And we can do that by using mouse move events at the very top in the window callback, or we can get the current mouse position by calling a Windows function. And I'd rather do that because it looks a little bit easier. It is easier. We define what is called a point, then we get the point position, or we get the cursor position from Windows, and then we do screen to client, which basically means it takes the screen position of the mouse and the window position and then fills in this point. And after that we store the previous mouse position, and then we store the current mouse position of the point. Basically, the previous mouse position can then be used to determine the relative mouse position. And that would look something like this. Only though we have to implement the i-vector2 binary operator minus, which means we have to go into the schnitzel-lib. Then we just yoink from the vector2 into the i-vector2 the minus operator. If you want, again, you can fill in all the operators. I don't want to sit here pasting all of them in, but basically this is what it looks like, the minus operator, and then we should have access to this right here. Now you might have noticed this screen to world coordinate function, which takes in a mouse position on the screen and then gives us a world position of the mouse. Basically what is happening is our screen, which we defined in the main now, is 1280 by 640. But our world is 320 by 160. At least that is the size that the screen of this size will display, or of any size. And in order to map this 1280 to 320, we want to use a function. And this function, in my opinion, should be part of this rendering interface. Above the rendering functions, there should be another section, which I call renderer utility. So this is the function that we're talking about. Basically, we want to take in a screen position, and then we use the game camera that we defined the last time. And then we take the position of the screen and divide that by the size of the screen. This will give us a value between 0 and 1. And then we take the camera's dimensions and multiply that by the value, which means that we have now effectively turned the X position into the camera space. But since the camera also has a position, we make sure that the camera's position is taken into account. And so we basically offset the X position by half the camera's dimension and the camera's position. So basically what that means is, the camera's origin point by default, if you don't move the camera, is 0, 0. But the screen's origin point by default is top left 0, 0. So we have this offset to overcome if we don't move the camera at all. And basically that is what this line of code is doing here. We're taking half the dimension of the camera. And if the camera's position X is 0, this falls away. And then we just get rid of half the dimension. So essentially what that means is, if our position on the mouse is on the top left, let's look in X coordinate. We go minus 160 to the left. That would be the top left position if we do not move the camera at all. And that's basically happening in X coordinate, and the same thing happens in Y coordinate. And then we return that position, and we are now in the world space, which is what we want. So if we go back to the win32 platform.cpp file, we will see that our screen to world now returns us into the world mouse position. And this is where I want to go into another discussion. I am returning a vector2 here, and I've prepared an image for you to understand what that means. If we take this picture right here, which is basically just like a tile set that is scaled by 2, right? If I take this tile set, is currently 60 pixels big, right? You can see that at the bottom here, or let's say, yeah, 60 by 61. Should actually be 60 by 60. But if we do and scale that up to 90 and then go over here, you will see that each pixel in the original image maps to 3 screen pixels. And if we return a vector2 here, then we are allowing sub-pixel movement. Basically, this is 1 pixel. We could allow something like the following. A pixel that starts 1/3 of the way in. And I'm torn between these two solutions. If I return an integer vector2, then we can only address the proper pixel locations. I can only address this 1 pixel location, and at some point I will move over to the next pixel location. And in this case scenario, in the Celeste clone, I think that is the correct solution. But it's not always the correct solution, which means that this is not set in stone, and depending on your needs, you might want to have a vector2 returned or not. I'm going to return in integer vector2 and then turn these floats into ints. In order to calculate the X and Y position as integer values, we first have to take the screen position and screen size as float values in order to get a value between 0 and 1. And then we take the camera's dimension, which is already a float value, and multiply that on top, which will then be converted into an int afterwards. If we don't do the float conversion here, then dividing something smaller by something bigger will always result in 0. And then at the very bottom here, this changed as well. After doing some calculations, this is the correct way to calculate the Y position. We need to take the camera's dimension and divide that by 2, which in our case would be 90. And then since we move the camera up by minus 90, we effectively cancel out the 90 with the minus 90. So the very top position of our screen is 0. We get to 180 at the very bottom. And now the mouse position should be correct. Now it is actually time to connect the input to the game. And first what I want to do is connect the input to the game the way it is. And then I want to create a generic game input type and then use that game input type in the game and bind the keyboard keys to the game input. In order to do that, I want to go into the game.header file, and inside the game state, we already have a player position. That's nice. So we take this player position, and instead of drawing the dice on 0, 0, we draw the dice on the player position, like this. And now you notice that it is complaining because the player position is an integer vector 2, but the draw sprite function only takes in a vector 2, which means I'm just going to copy this interface here and supply one with integer vector 2s. So essentially we draw the same draw sprite function, but before we do that, we convert our position into a vector 2. And now just drawing it at the player's position is boring, and so I want to do an input section where I gather input from the keyboard and then move the player. So essentially when we press the A key, we go to the left, we press the D key, we go to the right, W and S key up and down. And this is where we have our cube moving on the screen by pressing the WASD keys. But what if we want to do mappings where, let's say, we want to actually map this to the arrow keys? While we could do an if check here and then check whether the key is down or the key is down, then the key left. But that would be tedious, having to do this for every single key, and then if someone wants to change that, what do they do? And so this is where I came up with an idea of gathering input from the game and not really from specific keys. And so basically what we do is we define a game input type that could be move left, right, up and down, jump, stuff like that. And then we create a key mapping that is an array of key codes to keys. Or basically how that works is we define this key mapping at the bottom in the game state, and then each of these keys or types can index into the key mapping and then look at the array of keys that it is mapped to. And then each key knows whether it is pressed, released, just pressed, and all of this stuff. So we basically defer the call to whether an input is happening to the keys. And in order to do that, we need an array. And this is going to be the last big chunk that we are going to copy and paste in, which will obviously happen in the schnitzel lib. So we switch over to this, and then right below the logger is where I would like to put the array. Okay, so the array looks something like this, and I know I will get a comment. I'm not using an std array simply because I find this cool and interesting. You can use an std array if you want to, okay? I'm just saying that I like this, and so the way this works is an array has a type name and a number of elements. And this number of elements is stored when you create the array. Then we have a count variable and of course the type of elements as an array, a C array inside of the array. We override the operator, and on top of the operator I always like putting these assertions, so that whenever I access an element or try to add an element that is not the proper element, I get an assertion immediately inside my code that tells me, dude, you're doing something dumb. And then I also have some helper functions, like for example the remove index and swap method, which basically takes the current index's position and we copy over the last element into the position. Basically we are making sure that the array is packed. Helper functions like this are really cool, and this is why I define my own array. If you want, take a look at it for longer, but basically that is what we are going to be using. And then we should be able to switch over to the game. Yeah, and there should be no more error. Actually the game.h right here. So now we have the key mapping, we have the keys, we have the game input types. Now we actually have to check for game input. So in order to do that, I would like to add in another game function. This one is exposed, by the way. We expose this to the outside, but I would also like to have internal game functions that are not exposed, that are just inside of this game CPP file. And these are the functions that we need to define. For now, we have just pressed and is down. That basically takes in a game input type, and then it looks into the key mappings of the type, and then it iterates over all of the keys, and if it finds one key in the input that is just pressed, it will return true. Now you can also call the function here just pressed with the key, both of it works. And then the same thing for is down is happening. We take the type, we get the mapping, and then we loop over the keys. And this is how you can replace these calls then. And you know, there's going to be a magic cut here, like boom, and it's going to be like. So basically we turn all of this into is down, move left, right, up and down. But if we start the program right now, there's nothing happening because we also have to make sure that we add in the mapping when we initialize the game. And that is very simple. So over here where the game is not initialized, I want to create a section which adds in the key mappings. And for now I would like to add to the up movement the W key and the up key, and then to left A and left, down S and down, and right D and right. And now if we build and run the program, we should be able to move using the WSA keys, which it works. And then I use the arrow keys and I can move too. See that? And this is one way, obviously not the way, of how you can do an input system and at the same time key mappings. I hope you enjoyed the tutorial. If you have any questions, feel free to ask them in the comments. If you did like the video, please do leave a like and subscribe for more like this. In the next tutorial we will do something that is called auto tiling, which means that if we place a bunch of tiles next to each other, they automatically determine which tile sprite to pick. And I'll see you all in the next one. Peace!